But anyway, I'm delighted to be here, and I see you recording the meeting, which is great. So I'm a contributing editor at Sky and Telescope magazine and have been for about 7 years. And I wrote about 9 or 10 years ago, I wrote a program called RSpec to do spectroscopy of stars. It's something I had always wanted to do. And I'll tell you a little bit more about how that all happened as we get into things. In fact, let's one other brag about the software, and it won in like 2010 the best product. No, what was it? A hot product in Sky and Telescope. So people liked it, which is always nice as a single businessman, you know, and essentially just a guy like the rest of us, a guy or a gal. It was nice to get that recognition from Sky and Telescope. But more importantly, enough bragging about that. Let's talk about spectroscopy. Let me pop up the screen and get some things set up here. Okay, just getting my screen laid out. Can somebody shake their head yes if they can see that prism there? Great, thanks so much. Okay, so I'm going to talk for 45 to 55 minutes or so. Probably best to hold questions until after the presentation, just in that way we can really have a good discussion if something comes up. Let's see, what else? I think that's it, except I've got a little bit of a runny nose, but not to worry. I had my COVID test last week because I was down with a fever and scared. And the reason I mentioned that, you don't know me yet, so it's probably premature to talk about something personally like this, but if you haven't had a COVID test yet, someday, if you have to have one, I can assure you, for most people, it's nothing. You know, it's 5 seconds of you know, like, gee, I wouldn't want to do that again kind of things in your nose. But it's no big deal. So when you have that opportunity, maybe you'll remember these words. I was really worried. I kept thinking my friends were like being gentle, didn't want to scare me when they told me that, but it's really the case. Okay, so let's get started. How have we managed to discover so much about the universe when really we haven't even left home, right? Images, of course, we've been capturing for a long time now, and they tell us some things that our bare eyes can't tell us. And we can also get, even bare-eyed, fleeting glimpses of a third dimension during eclipses. And for a fourth dimension, if we wait a while, time comes into play, and you can see maybe up there in the upper right-hand corner. Sometimes I find my eyes these days, you know, with an image changing like this, I can't find what's changing, and I'm looking all around. That's why I cue you to the upper right-hand corner there. But if we spread the colors out, we get an as-if fifth dimension. It's gorgeous aesthetically. And those gaps reveal a barcode for our sun or for whatever star or whatever object we're looking at. And they can tell us something about the material. Again, you can see a list there of bulleted items. I'm not going to read them aloud, but I'll show you examples of some of these this evening. So even if you're not a backyard imager, or maybe you don't image at all, I'm going to list here some things that I originally wrote here because I wanted people to understand what my goal was in the talk. There are going to be a lot of words on this page, just single sentences. But even if you're not imaging, I think you're going to find our discussion interesting and helpful, because a huge percentage, an enormous amount of astronomical research gets done with spectroscopy. So even if you're an armchair astronomer and don't even have a piece of equipment, to be able to understand some of the things that we see in the magazines we read and the websites, it's helpful to know how people do this kind of stuff. So bear with me as I try and race through this initial material. For those of you who are imagers or used to, maybe you remember that first image you captured. For me, it was the moon. It was god-awful, overexposed. It was blurry. My tracking wasn't any good, but it still was the most beautiful moon photo I'd ever seen. My wife heard about it, my friends, my colleagues, they'd had enough. But of course, thrills being what they are, it did fade. And so I wanted to recapture that thrill of excitement, of discovery. And I found that spectroscopy really delivered the goods. Maybe you want to do some new science. That's what I wanted to do in about 2009. Maybe you want to contribute to science, and there's opportunities to do that also. None of us like to spend a lot of money ever, let alone when we're not sure we're going to like doing what we're going to do. I'm going to show you some things tonight that are really inexpensive. I think this is the most significant point. Again, I'm just going to keep racing through this. And that is, when you own the data, especially if you captured it or if you just have it in your hands from somebody else, your whole relationship changes with it. And that's because you have an interest in it. You might want to Google something about it. When you read things, they actually stick in mind. I know these days a lot of things go in one mind and out the other, or one ear and out the other. So owning the data changes your relationship to it. You don't have to travel to a dark sky site. I'd hope to chat before the meeting with some of you and hear a little bit about your observing programs, and if the club has a dark sky site. It sounds like maybe that's what you were talking about. Because visual imaging is so sensitive to urban light pollution, we tend to get gun shy about starting anything where we need dark skies, and this is not one of them. This is something, because we're not involved with all the color balance and all of those issues and wide range of exposures and brightness and dimness. So this becomes much easier. Well, I'll just show you some examples in a minute. Thank God you don't need a PhD in astrophysics. I don't even have an undergraduate degree in science. But if a knuckle-dragging programmer like me can learn and enjoy this stuff, anybody can, I assure you. And the cool thing is there's no exams, there's no quizzes, so you learn as much as you want. You're going to hear me talk tonight as if I know what's going on. And really, this is not false humility on my part. I'm like a really broad river that's really shallow. So during the Q&A after my talk, you can discover just how shallow that river is. I was a terrible imager when I imaged. I just did not get into it as much as a lot of guys and women do. You need a lot of things, equipment, patience, skill, dark sky sight, all that. Fortunately, there are people who want to do those kinds of things, and we get to enjoy their images, but it wasn't for me, and I'm going to show you things you can do with just a video camera. I'm not a do-it-yourselfer. I break just about everything that I touch. In fact, edit, undo, or Control-Z are my favorite commands in Word or in Windows in general. And fortunately, you don't have to build anything here. It's all off the shelf. If you do outreach, and I bet some of you do, public outreach, this is a great kind of project. And I'll try and remember to point out some screens that can really help if you're doing some sidewalk astronomy or a first quarter star party somewhere. If you want to mentor students, it's a fantastic project because it's tough, to go into a physics teacher or astronomy teacher and talk about what you can do with their students. I mean, yeah, you can observe some things, maybe photometry if that's your bag, but what I'm going to show you is real science and science that high schoolers can handle. With your equipment and experience, you can really catalyze and change somebody's life and also enhance yours in the giving, as you'll see. And finally, maybe you want to do spectroscopy because you want to hang out with the cool crowd. That's not me, but there are thousands of amateurs doing this kind of thing today. And the reason I mention that is that means that online there's forums, there's readily available information. And it also means you're not on the bleeding edge, right? You can actually do something. So let's dive in a little bit and talk just a tiny bit about the science just to get everybody to somewhat the same level. Sir Isaac Newton discovered, and many of you will be familiar with this, and I apologize for that you can split white light in a prism and get its component colors. You can also do that by bouncing light off a finely lined surface, like that DVD there, or through a piece of glass that's finely lined called a diffraction filter or grating, and that's what we're going to talk about tonight. Now, Bunsen invented his Bunsen burner to burn stuff, obviously, but he wanted to burn elements and see what their spectrum looked like when he passed the light through a prism and then observed it from here. And he burned everything. He was a real pyromaniac. And the great thing is he kept a catalog, which really served subsequent decades and generations and literally centuries. And we'll look a little bit at that catalog as we go forward. Kirchhoff was a colleague of his. I'm not going to spend a lot of time talking about it, but just one quick thing on this next slide. And that is, notice this spectrum here has gaps, and in the background, it's got a rainbow, right? In Roy G. Biv color, starting with red, red, orange, yellow, green, blue, indigo, violet. So that's an absorption spectrum because there's gaps. You can also get a spectrum that has a more or less dark background and just some lines. Now, regardless of which one you get, those lines are going to be in the same position. So it doesn't really matter for most of what we're doing, which we're looking at. Which you get, an absorption or an emission spectrum, depends on things we won't discuss tonight that Kirchhoff got into about the temperature of the gases and pressures and stuff like that. So, but these gaps or lines are like fingerprints. So it's become, you know, there's people teaching this kind of thing in colleges, community colleges, even liberal arts students are doing this kind of thing now, and I'll mention that in a minute a little bit more. And one of the professors, actually at the University of North Texas, Ron DiIlio, now a good friend, he's got 8 C8s, or it was 5 C8s, I think. I actually flew down, they're in Denton, to you know, look at their setup, because he runs 2,000 students a year through a lab that they do doing spectroscopy. And he called it the CSI effect, the fact that all these students are sort of into this now. Like, it's sort of cool because they've been watching CSI and shows like that where there's forensic analysis using big scientific instruments. So that's what this is all about, is basically analyzing these lines. Now, hydrogen's so common in the universe that we've actually given the lines in hydrogen a name, hydrogen bomber lines. And we've given them Greek letters like we give the stars by brightness in a given constellation. I'm just sitting here thinking, you go from this, you know, sort of discussion before the meeting, you know, people are sort of kicked back, you know, you introduce me and it's like the fire hose got turned on. So forgive me. Like I said, there won't even be a quiz at the end of this. If you come away going, that's pretty cool, I understand a little bit more about how scientists do things, or if you come away going, I'd like to try that, that seems pretty easy, that's really my main goal here. If I can, you know, make you crack a smile a couple times tonight, that's a bonus that I really like. So these labeled Greek lines, alpha and this beta, what is in robin egg blue sort of color, we use as beacons or lighthouses, as you'll see in the next few slides. Here's a periodic table. Some of you are going, oh my God, this is going too deep. Well, we're not going to do much here except to look at the fact that hydrogen, there are the lines, that hydrogen alpha in red and that robin egg blue beta and so forth. And you can see they're very different. Here's the helium that you'd put in a balloon at a florist, for example, or even down below hydrogen here, the lithium that's in the battery of your cell phone. They all have different lines. I don't encourage you to say burn the battery in your cell phone, but that's what somebody in a scientific setting would see. We don't have to burn things anymore, thank goodness. Over here you can see, and this is my software, you can see a live video feed. In fact, this is just a gas tube here that's in, you can see that's actually a hydrogen gas tube. See if I can get it out of here without shocking myself. It's just like a neon or, you know, fluorescent tube of some sort. I don't know whether you could, I've never been able to see whether you can actually read that HE there, maybe. So that's our helium. So, and you can see, well, in this case, it's a bad example because this is a hydrogen tube. There's that red hydrogen alpha and that robin egg blue hydrogen beta and so forth. And I mentioned a little earlier UNT. This isn't a slide especially for a presentation to Texas. This is a slide I always show. It's a little camera that I mean me, created for physics and chemistry and astronomy classrooms. It's quite popular, actually. So Auguste Comte, we're going to jump around a little bit chronologically, in 1835 said, the stars are too far away, we'll never know what they're made of. But it wasn't a few decades later that all sorts of people were studying the stars with spectroscopy. You know, the science had advanced. When Auguste Comte said this, they didn't know that spectroscopy could be used in the way we're going to talk about tonight. So far, everyone I've talked about has been an old white man. So I wanted to show some of the non-old white men who've done amazing things in the field. First of all, you may have heard of Annie Jump Cannon. She and her team of computers, women, that's what they were called, computers, it's an interesting term back then, they were prohibited from accessing the telescopes at Harvard. So what they ended up doing was studying the glass film plates of spectra, and they were really fantastic at it. They did hundreds of thousands of these studies, and again, through their insight, diligence, and really just smarts, came up with a star classification system that was far superior than any previous. In fact, the ones previous just didn't work. So Priyamvada Nataraja she's at Yale, and she studies hypermassive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the late 1940s. And she was also a big proponent of the Hubble Space Telescope, which you see there. Elisa Quintana studies exoplanets and found one in a region that would be have liquid water but not frozen or vapor, and it could be an exoplanet with life given it's got liquid water. Jedediah Eisler's she's at Dartmouth and she studies gravitational lensing in black holes. So we've come a long way. There's a long ways to go yet, but I wanted to highlight these women. It was a fun slide to put together this past summer because there's so many others out there as I was digging around on the web who are doing really amazing stuff. A little bit more science here. How do we get these gaps in these emission lines? You may remember Niels Bohr talked about electrons circling in numbered orbits. And when an electron drops from one orbit to another, it gives off energy, which could be visible light. Different drops, say, for example, let's look at this one. This one here is from level 4 to level 2. It creates, well, that's that robin egg blue hydrogen beta. So when an electron jumps up, because it has to be pumped up to drop down, when an electron jumps up, it absorbs light. And so you can see there's the gap of an absorption spectrum. So here's the Hubble Space Telegraph. Telegraph. You can tell where my mind is. I haven't sent Morse code in several decades, but I was a ham at one time. When the space shuttle was servicing the spectrograph, you can see it there. There's the astronaut moving the instrument around. Let me tell PowerPoint to leave the arrows up. So there, my cursor will remain visible. My grandson says, that's not a scientific instrument. He says that's a refrigerator and it's filled with beer because on the space shuttle, when it was night, they were real party animals. And you know, you get a lot of nights when you're going around the earth that many times in 24 hours. He knows better, but we have good-natured discussions about that. Here's a rather complex device, a nice mount, a big telescope, lots of wires. But what I'm going to talk about mostly tonight is this little grating here. It's called a star analyzer grating, and it sells for about $200, 1.25" threads, and it'll thread onto almost any camera. So here we've threaded it onto the lens cap threads of a DSLR. And in less than 30 seconds on Vega, we can see the hydrogen alpha. There's the hydrogen beta in the robin egg blue and the gamma. So the reason I show this slide isn't to encourage people to do it this way. Notice there's not even any tracking here. So it's a little challenging with a small aperture, and without tracking, you've got to get things lined up right. But to point out, there's no magic here, really. There's no mysterious black box that you can't open or that you have to finely tune. It's just this diffraction grating. So here's some examples of how you can mount it. This is the one we just saw. And we actually sell for like $40, this little thread adapter to thread it onto the lens cap threads of a DSLR and then the 1.25" threads here. And these can produce, especially with tracking, a pretty high resolution spectra, higher than when you put the grating elsewhere. The light goes through the grating first on this. It's called an objective grating. Here's a DSLR. It's not a DSLR. It's a FITS camera. Could be cooled, maybe not. On the bottom right there is a ZWO camera. The grating often just threads right on to the lens cap or to the adapter or nose piece threads. And we'll look at a little bit of that later on. Can be color, can be mono. Of course, mono is more sensitive. And down here in the lower left is just to point out that you can even put it inside a filter wheel. So there are more expensive devices. I'll show you a handful of examples from these. They're higher resolution, also an order of magnitude more expensive. And not only are they more expensive, but they're also considerably harder to use because you're using a really narrow, like 20 micron, 20 millionth of an inch slit. Imagine, acquiring your target and tracking on something that small. You can build one yourself if you're into 3D printing. They're considerably less expensive, still somewhat hard to use. You can piggyback a DSLR on your current telescope if that's the way you want to go and do two different types of imaging at the same time. All right, thank you for letting me zoom past all that. It was, just like I said, the foundation to help us all be able to talk about the examples I'm going to show you. So we take a star, we put the light through a grating, and we split the light like it's a prism. going through a prism into this spectrum here. So that's some of the starlight that went straight through without getting bent, but most of the starlight gets bent and becomes that rainbow. So let's look at a really great example. So this is different spectra captured by Torsten Hansen with an 8-inch Newtonian in one of those imaging source video cameras, like the ZWO camera or Malin cams, those kinds of cameras. These are a little older. So, and these are in temperature order. So these are the hot stars, type Bs there, and it gets cooler, type As, type Fs, Ks, and Ms down to there. So look at the differences. You know, one of the bullets I showed you earlier talked about being able to tell star temperatures. This is how professionals do it. They look at the different lines, absorption lines in this case, gaps, and they can tell that something about the temperature of the star. And so can you, and so can we. So two quick examples here. First, notice that I wouldn't call that a line. That's like a forest of trees, right? Well, and it's only really on these cool type M stars here. So these are caused by an actual complex molecule in the outer shell of the star. And the star's relatively cool, so it doesn't get burn up. It actually can absorb some light as its electrons are jumping around. The second example to show you are these lines in the 4800 region in, well, the robin egg blue, right? The hydrogen beta lines. And I wanted to show you, remind you, that we talked about how electrons jump between shells. They jump up and then they fall down, right? And when they fall, they absorb energy. That's what these lines are about. So why are they different on different temperature stars? Well, this type A star, which is like Vega, seems to be the most prominent, widest, darkest absorption line. So that's okay, but why are these dimmer on these hot type B stars? Well, because these hot stars are so hot that the electrons often go right past that level 4 as they're pumped up, so they can't drop from 4 to 2 because they've already gone higher. So you don't have as many electrons in that shell 4 to fall down. And these cooler stars here, a lot of the electrons don't even get pumped up to level 4. So again, there's fewer, in fact, down here, it looks like almost none dropping from level 4 to level 2. So this is the first time I've used this diagram on the screen. In the past, I've always tried to draw it. I spoke to a club in the UK at lunchtime today, and I said, this is enough. That's hard to draw on the fly while you're talking. But again, that explains a little bit of the differences that you get from different temperatures. Now, my wife always insists that I dress for success. So I wanted to show you here. Here's the hydrogen beta, or no, that's the alpha in the red. And if you look down deep, I know those of you playing at home are going to be familiar with what I'm about to say. It's a mess. My salon hasn't been open. They're not picking up the phone. And the problem is when you look down deep, you know, we're all about color and spectroscopy, right? It's no longer red down there. It's sort of gotten a little gray on me. Like I said, I know some of you have experienced this firsthand in your households. So not to worry, hopefully that'll be a problem that's behind us fairly soon. So by the way, my wife, when she saw I was doing this, was not amused. She didn't beg me, but I like to say it. She doesn't beg, she doesn't have to. But she did beg me to not do this. I figure, listen, if I can get a smile out of you, whether you're laughing at me or with me, the idea is that I've just loosened some dopamine drips in your brain. You're a little bit more refreshed. Maybe I'll be able to entertain you for a bit while longer before it gets too late to keep your eyes open. I know it starts getting late here when we get into the evenings also. So you see that crosshairs there? Maybe you can see, and I'm not asking that facetiously or rhetorically. There's a little dimming there. But, you know, suppose I got time on that Hubble spectrograph. God knows how. And I wrote a paper on the results. And, you know, the paper read, and, you know, we observed such and such with the Hubble spectrograph, and we saw a little bit of dimming in the robin egg blue. I wouldn't get published, right? So in order to be publishable and scientific, we need to be quantitative. And for that, we just make a plot, make a graph of the intensity of this region, and that's what the plot looks like. So this axis here is how bright is it? And you can see the stars really bright. That's the light that went straight through the grating without getting deflected. And the star's really narrow, so this is a narrow high peak. And this thing, it's pretty dim out here, and then it gets brighter, 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 and then dimmer, dimmer, dimmer. So this is dim, brighter, 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 and then dimmer, dimmer, dimmer. But look at this. See that dip in the graph? Even if you can't see that dimming there, you can easily see the dip. Now we're doing science. Now we can measure the full width half maximum. Where is it located? How does it compare to other stars, or this stars at other times, or other instruments? That's science. So how do we get the graph? So my story is I wanted to do some science in 2009. I got a grating. I went outside in my backyard here in Seattle. I forgot to mention that's where I am, I think. Right outside in the yard there. And I actually found it 2 days ago while I was cleaning up. I had this Logitech webcam. You can even see the duct tape from attaching it to a barrel off an eyepiece. Somehow I got the whole thing to work. I came in at midnight. My blue jeans, they were grass stained on the knees. My neck hurt because I was looking at Vega overhead in August. You know what that's about. And the next morning, Sunday, I wanted to, take this, and this is actually a frame from that first video, and create a graph. And I couldn't. I downloaded some freeware that was out there. I tried it. It was crashing. I had a heck of a time installing it. It was crashing. Half of it was in French, literally. There was no manual, and it just wasn't up to the usability standards that we've become accustomed to. So I'm embarrassed to admit I quit. I told my wife, this is a hobby. I'm supposed to be having fun. I work during the week. And so I just put the grating in the drawer. I figured I'll have to figure out something else to do. This seemed like it was going to be fun. But it kept weighing on me because I really wanted to do this. So I figured one day at lunch, I said, okay, Saturday, I'm going to write a program just to create the graph. How long can that take me? And next morning, Sunday morning, it was done, and I had this graph. Now, 10 or 15,000 hours of programming time later, I'm almost done. It became popular. People wanted to do it. I enjoyed helping people get started, and so that's what I ended up doing. So, I think one of the obstacles that we all face when we're going into some new aspect of, well, whether it's astronomy or other things, is, oh no, another program I'm going to have to learn, climb up the learning curve. And that's a real obstacle. So, and the reason I mention it is I'd like to show you just 2 or 3 minutes worth. I know that if it's longer than that, instead of seeing people's faces here, I'm going to start seeing the tops of people's heads because they will have nodded off on me, right? And that's understandable. So I'm going to keep it to just a couple minutes. And hey, Linda, you're there. Could you count? I'm sorry to put you on the spot. I shouldn't do that. Just count the number of clicks I do. I'll call them out because I think it's less than 10. So this is, I'll let you know when I click. I'll try to anyway. This is an image from that video. This is a single frame. It could be a FITS image that just automatically loaded into the software when it hit your hard disk from whatever imaging software you're using. I like color here for outreach and education because it's more intuitive what's going on. There are some gaps there. There's a gap there. So what's the first thing we do is we have to tell the software the area that we want to study. So there's 1 click, 2 clicks. I've now bracketed in a region, and we can see on the right that intensity graph, right, Linda? We got 2. So there, that peak there is the brightness of the star, and this thing is that thing, and that dip is that gap. Pretty cool, huh? So what? It's a bunch of dips on a red line. Remember, I mentioned that Bunsen kept all these catalogs of things that he burnt. Well, we can use that catalog's great-great-great-great-great-grandchild. It's been enhanced a little bit, but same data, really. Let's look at that in the software, and we can come down here and say, show me on the graph, when I check this box, where the hydrogen bomber lines would be. Where would there be gaps or dips if it was hydrogen causing these features? And look at all the matches we got there. Hydrogen alpha, hydrogen beta. So the fact that our red data really matches up with this reference data is pretty remarkable. pretty good evidence that we're observing on Vega, my first night out, the impact of the light going through the hydrogen as it left that star, 25 million light years away. Isn't that amazing? Next click here is to give you a little eye candy, right? That's sort of nice. And then this is actually a freeze frame from a video that I made that first night with this stupid Logitech camera. So, and I'm going to play that video so you can see it in real time. And this could be under the stars. Again, our image is jumping around. That was another click, by the way. And you can see my data is jumping around. This could be real time. You could be doing this at a star party. You could be doing this at an outreach with the public. So it augments the other observing that you're doing. And it gives you a springboard to talk a little bit more about the science. And you don't have to go into a lot of depth with the public, as I'm demonstrating here, because I know very little, and some of you probably know more than I do. That's okay. You're just sharing your excitement and enthusiasm for science. So one thing that's interesting is, notice, let me turn off these lines. Oh, okay, those are 2 more clicks. Notice this feature here is coming and going. Thanks, Linda. It's coming and going. And you can't quite see it all the time. Well, a lot of us are familiar with the idea of stacking images where you add them together to eliminate noise. I'm going to do that in the software. So this video is playing at 2 frames a second, and I'm going to stack by clicking that. Look how quickly that image stabilizes. The feature becomes very clear, symmetrical, somewhat Gaussian. Isn't that cool? Real visual demonstration of stacking. Okay, so I'm going to pause 1, turn fill off 2. That's a double click, so that should be 2 clicks, because we're done with this screen. The one thing I wanted to show you, this is cheating, I'm going to turn that back on, is if you would, in your mind's eye, just remember this view. You know, it's Vega, and the key here is that we have a reference library that's telling us where the hydrogen alpha, there's the beta in the robin egg blue, and gamma, where those lines would be. So this is from that Bunsen-like library, but we're going to see an example where this data is actually used in professional research as we move ahead. Okay, how many did I have, Linda, do you think? All right, 8. Terrific. Thanks for counting. I'm sorry to put you on the spot. So it's one way to stay awake. You get that jolt from a speaker, you know, that just like pops us all awake. Okay, so let's go back to the show here. So that's how you create a graph. Here's some more of that outreach that I mentioned. This is initially of gas tubes, and then they transitioned to Vega or something like that. This is actually in Marseille, France. And you can see, you probably wouldn't want to do this. Let me get that cursor sticky again. Microsoft, when will they get it together? This isn't sticky. Every time I start the show, I've got to set that again so my cursor doesn't disappear. Not that I'm complaining or anything. So you wouldn't want to do this at a dark sky party because there's so much light on that screen, but for outreach, why not? So here's a DSLR image. You can see 3 stars here, and you can see their respective spectra, and there's a gap. We can see a star here, and look, well, those are lumps, aren't they? Well, these are emission lines, and they're so bright, they just saturate the pixels and spread out a little bit. But let's look at a Wolf-Rayet star for a second. When Janet Simpson sent me this, I have a confession to make to the group tonight. It's a real confession. I couldn't remember what a Wolf-Rayet star was. You know, I'd read about them, you know, maybe not countless times, but a half a dozen times or more over the 20 or 30 years I've been doing this. I couldn't remember. But the good news is Wikipedia is your friend, and Wolf-Rayet stars are late stage stars probably heading to be a supernova, and they have really strong stellar winds, so the outer shell is getting dissipated, and you can actually see a little bit into the star. Here's what the spectrum, here's what the spectrum looks like. Carbon emission line, carbon, carbon. Why would we be seeing carbon in a star? Well, remember, stars burn through their elements, starting with hydrogen, going to helium, and part of that fusion process involves carbon. So we're seeing that with 30 seconds of exposure time on DSLR. With a mechanical tracking, that's really all you need. Isn't that amazing? So let's look at another emission object, our beloved Ring Nebula. That's a little different looking, isn't it? Well, fortunately, the Ring Nebula really only has 2 emission lines, hydrogen alpha, and this is oxygen. That Roman numeral 3 just means that some of the electrons have been pulled out, have been ionized. So, but most extended objects that aren't point sources don't look really very good in a slitless device. So let's look at an extended object with a slit device, our beloved Orion Nebula. Certainly extended, right? It's huge. Same features, hydrogen alpha, ionized oxygen, there's that Roman numeral 3. Notice we can see other features here. That's what a slit brings you. So I thought I'd stop screen sharing just for a second, because I really enjoy this next step. I'd like to ask if anybody wants to, and that's okay if you don't. This hat gets hot after a while. So I'd like to ask if anybody wants to share with the group their first experience seeing the Orion Nebula. Where were you? What kind of telescope? What was that experience? Anybody want to unmute themselves and share that? It's okay if nobody does. But, you know, for many of us, that was a formative experience of some sort, either positive or negative. Oh, there we go. Hey, Jerry, go for it. Thank you.
We were just setting up our telescope that hadn't been running for 12 years, but it was a new telescope. And I had several people there who knew a lot more than me because I just wanted to see it run. And the guy who brought our camera, it's a QHY, can't remember, 183 or 163C. And so he was setting up the camera. The scope had not been balanced and it needed several things. And so we were there maybe 6 hours. But when we turned it over to Orion on the nebula, it just popped in. And Bruce, the guy who brought the camera down, got so excited. He says, "Man, that's a wonderful picture. That's a great picture." And then we experimented with different settings on exposure time and adjusting the camera's light settings and so on like that. It was really amazing, and I still have those pictures. I still show those pictures all the time.
That's great that you still have them. That's wonderful. Anybody else, perhaps a visual experience before you had a camera? All right, no big deal. Let me share my screen again. So my experience was, it was in the early 1990s, and I wanted to observe Shoemaker-Levy 9. I heard it was coming. I went out to the Denver Astronomical Society urban first quarter star party. You know, it's fun when you can remember when you didn't know something. And for me, I walked out on that observing field, and what I saw, you know those cannons in the circus that they use to shoot people out of? That's, to my uneducated eye, that's what I was seeing. So of course they were Dobbs, but I didn't know any better. So I queued up. There was somebody much like some of you or me running the telescope, running a Dobb. They were all excited. It was, you know, M42, the Orion Nebula. I'd seen pictures in some magazines. I got up to the eyepiece and I was really disappointed. I mean, it was a smudge, right? It was nothing. Thank goodness I stuck with it. I don't know quite why I did. I think it was the Shoemaker-Levy 9 was getting me excited, because this certainly didn't excite me. So, but I'll tell you, and some of you may have had similar experiences early on. I've had guys telling me about a Tasco telescope they set up, just in December, and it was 10 degrees out. But the thing is, many of us who had that experience still come back and look at M42. Why would we do that if it was just a smudge? Well, of course, we've got better telescopes. We might be in dark sky sites. We've also gotten better at averted vision, right? We know how to observe stars out of the periphery so that we're able to, see things a little bit more dark or dim. But I'll tell you, and you all know this, the more you know about the object you're looking at, the more interesting it is to even visually observe it. And so that's what spectroscopy has done for me is I'll see something like this and I'll go, well, maybe I'll read about the Orion Nebula in some little stick this time, why those are there. So I just wanted to share that because it's one of the things that I think really has been really nice and a surprising thing with spectroscopy. So here's Uranus and Neptune's spectra. You can see some big gaps there. They show up in the intensity plot. We're seeing the atmosphere, the methane in the atmosphere. This is also by that same guy who did that multicolored one. with just a video camera. Imagine seeing the atmosphere of a planet in the backyard with a video camera. So, you know, when we discover life, if we should, whether it's on Venus with phosphine or whatever, it's probably going to be with spectroscopy by observing things on the planet that we don't think could have been produced in any other way but life. It's a big step to make that conclusion, but that's the direction we're going to be going. So, in 1881, Henry Draper, that's the catalog guide, observed a comet. It was important enough for the New York Times to actually publish an account of that. Here's a comet spectrum here. Notice that nice string of gems. And there you can see the intensity plot. Those are called the swan bands. They're mostly carbon. This was captured by a guy in Northwest India, a nuclear power plant engineer, who in 2013 was a real beginner. Now he's a real expert, and I learned from him. And what teacher doesn't want to learn from their student? That's a real win. So here's a more contemporary example of NEOWISE. You can see this peak here for this yellowish tail. So, and this was done with an objective grating, just with the star analyzer, just threaded onto the nose piece, lens cap threads of a DSLR using this little adapter. So, anybody who uses a C-clamp as part of their setup, that's my kind of amateur, right? Of course, if it was me, I told you I already break things, right? So I'd crank it down too tight and the enclosure would buckle and I'd destroy the camera. Fortunately, that's not what Robin Leadbeater did. He put a star analyzer on the nose piece of a video camera, and he actually designed the star analyzer and is a real expert and does a lot of pro-am collaboration, professional amateur collaboration, and helps a lot of us in a lot of ways. Really brilliant, nice guy. This is a single frame from that video, and you can see during that one frame, the meteor traveled that distance. This is the spectrum, and you can see, for example, that gap there is that dip. This is a rather esoteric way to do spectroscopy. You need to find the meteors first. But again, whatever floats your boat. So I'm not going to talk a lot about the flash spectrum. We've heard a lot about it 2 years ago, and we're about to hear a lot more about it, except to point out that we discovered helium on the sun before we ever found it here on Earth. It's a remarkable discovery. We don't have time for it, but fascinating story. If you're using a DSLR on Novae, you can see some have this deep dip that has iron, that indicates iron. This one doesn't. Just a quick review about Doppler shift. If a car honks its horn and you're standing here, the car is coming towards you, the horn's going to be a little higher pitched. If the car's moving, that's the first time I've tried that. If the car is moving away from you, it's going to be a little lower pitched, much like a train going through the station with its whistle, right? High, low, high, coming towards you, low, moving away, moving away. In fact, you can do that in your car tomorrow when you're driving. Just roll down the window and listen to the swishing sound as cars go past you, or trees, or almost anything goes past you.
You're home early.
Somebody could mute their mic, that would be great. So maybe our meeting person can mute all the mics, mute all, and then I'll unmute mine. There we go. Thank you so much. So that swishing sound from high to low is Doppler shift because you're moving past the sound. So suppose we were expecting this triplet. I love that word. It's self-describing, isn't it? And we were expecting it right there where I'm pointing, but instead we found it over to the side. It shifted in this case towards the red. So that would be redshift, and that would indicate the object's moving away from us. On the other hand, if it was shifted to the right, left, I'm doing a lot here trying to get my directions right so that you're seeing them in the same way that they're showing up on the slides. This would be blue shift. So I want to talk really briefly about different types of supernovas. There's one called a type 1a. We're not going to get into a lot of the details except that some big old star ends up dumping some gas onto a small white dwarf. And when you dump gas onto a hot surface, it explodes, right? So here's one in M101. For a brief time, this star shined more brightly than any other star, all the other stars in the galaxy. There's an example of another type 1a, not this one. This one was closer some decades ago. And you can see it sort of looks like a sphere, doesn't it? Like it's a blowing up sphere. Well, David Strange in the UK used a 9-inch SCT and less than 15 minutes of integration time to stack some images and get that spectrum. Now, again, same drill. Maybe you can see that dip there, but now you can really see it. That's why we plot things on a graph. Now, you know, it's overused and soon to be yet one more time overused. We do stand on the shoulders of giants. The giants figured out that there's actually a signature for different types of supernovae. So there's a different type than this binary star, but the binary star creates a big dip right around 6,000. This won't be on the quiz that you'll be getting later tonight, but here for a type 1a, there's a deep dip. It's at the right silicon wavelength, right around 6,000. Notice that these other types of supernova, there's some that they run out of fuel, the star runs out of fuel and it just collapses on itself and so forth. None of them have a really deep dip in silicon, but they all have some unique signature, some line that the others don't have. So David was able to identify this as a type 1a supernova, and that's one way that amateurs can contribute to the scientific efforts that we make. Oh, by the way, speaking of efforts, I wanted to mention when Bunsen invented the Bunsen burner, he proclaimed that he was not going, and he didn't patent it. He said, I want this available for the good and benefit of humanity going forward. It's a remarkable sentiment. Of course, today there'd be, I think I said sediment instead of sentiment. Sediment is what you're getting from that leaky pipe. Sediment is, again, here we can see this deep dip, and professionals want us to help identifying supernova. It's not as easy as it might sound because there haven't been any local ones in our galaxy in a long time. They're quite dim because they're extragalactic. But here's what he and I did real quickly here. We measured the wavelength of that dip. It's right around 6,000 like we expected. We wrote it down. We looked up what silicon, that's what it is. If Bunsen had burnt beach sand, he would have seen it at that wavelength. Look at that difference there. That's Doppler shift. I couldn't remember the Doppler shift formula. I'm giving myself credit when I say I used to know it. I don't think I ever had it memorized. It's pretty simple. When you plug the numbers in, we're now calculating the blue shift from the shell of that expanding supernova as it comes towards us. It's a huge number. And we did it with a backyard telescope. We were able to measure that. Isn't that amazing? So you may recognize Adam Rees's name. He and his team researched just before the turn of the century, the accelerating cosmological expansion. And they used type 1a supernovae as standard candles. Somehow, I don't think they used a grating like this, but it's remarkable what can be done with something so simple. What about the spectrum of a black hole? Well, of course, a black hole doesn't emit light, but the matter, the accretion disk that's spiraling in does. And because it gets very hot. So David Hayworth in Portland, Oregon, observed a quasar. There it is. I've never observed a quasar. There is a spectrum. You can see two little dots where those arrowheads are on the right. There they are, blown up. And there's the spectrum. So this guy was 25 years old. I thought I saw some younger faces here. Maybe Bear, maybe some others. I'm not going to call on anybody else. I'm sorry to have done that. I always sit on the edge of my seat if I think somebody's going to call on me. He was 25 years old in the mid-1960s, and he looked at this and he said, well, what are those peaks? And he got really frustrated. He couldn't figure out what they were. He said, okay, I'm going back to square one. And he said, much like in a lot of science, what we do is we eliminate things that they can't be. So he said, well, I'm going to prove they're not hydrogen. Let's get past the common stuff. He brought up a reference, and this is what I asked you to keep in your mind's eye from my software. And you can see some reference lines there for hydrogen. There's the robin egg blue hydrogen beta. But he was relieved. He said, well, these lines don't line up with those peaks. So we know that these aren't caused by hydrogen anyway. Except they were massively red-shifted. That meant this object was moving away from us at enormous speed. And using the Hubble constant, we could calculate how far. What's astonishing to me is that this light, which has traveled 2.5 billion light years over, a long period of time, still had enough information in it that we could tease out something about where it originated so far away and so long ago. But light didn't seem to age, did it? Now, humans don't do so well. Here's Martin Schmidt a few years ago. I have been justly accused of throwing rocks in a glass house when I show this second photo. And it's true. Look, he's got a full head of hair. I'm envious of the guy. So we've got 2 more quick examples and we'll finish up. So far, and by the way, just to remind you, that was a quasar, The remarkable part about that discovery that he made, and the reason I knew a little bit of the inner story is because there's a transcript of a wonderful interview with him. It's linked to from my site. I'm happy to send you the link if you can't find it. There's a contact form on our site. I sound like one of those TV commercials with the little footnote at the bottom, at the very end where they speed the person's voice up. The amazing thing about his story is that when he discovered this, he was really, like all of us, a little nervous. And he was nervous that somebody would look at his publication of this, that he was reporting these were bomber emission lines, and go, oh, you're so wrong, man. You made such a rookie mistake. It's so obvious what those lines are. Why are you trying to force this massive redshift on this thing? So he called his colleagues in. They all agreed with him that this was that. He went home. He told his wife that night. He said, something terrible happened at work today. I think he doesn't talk about it any further in the interview. I think he realized what the notoriety was going to do. And being a celebrity isn't fun, I don't think. I'm assuming. So the remarkable thing about this discovery wasn't that something was that far away, but that it was that far away and so darn bright that we could even see it here. It had to be enormously bright intrinsically. Okay, so as I mentioned, so far we've been studying these hydrogen bomber features, alpha, beta, gamma, and how wide are these features? So let's just look here. That feature is how wide? 40, 50, or so angstroms on this x-axis here. So if we wanted to look at the detail in this hydrogen alpha line, we can't just use our mouse roller wheel, can we, to just zoom in? It's much like, imagine you're observing the moon. And if you're like me, when you first did it, you started throwing on more and more magnification. I really want to look at those ridges or those, whatevers. But beyond a certain point, it's empty magnification. The same thing goes when you're using any spectrometer. There's only so much data there. So to drill down and look at the details here, we come over here with a slit spectrometer. Now you can see the blue is the moon, which isn't really moving towards or away from us. And the fuchsia is, what is it there? Is Vega. See the offset? That's the radial velocity of Vega that we've measured with a backyard, again, a little more expensive and hard to use, slit spectrometer. We had to measure an offset of 0.67 angstroms. On this scale, that'd be a heck of a lot of zooming, wouldn't it? So final example, I've got a visual aid here. This is a star. It's spinning very rapidly. So as it spins, let's say it's spinning this way. I need to take Harlem Globetrotter training so I can do this on my finger. This edge, as it spins, the light coming off that is a little blue shift, right? Because it's coming towards you. Whereas this edge, the light coming towards you is a little red shifted because that edge is moving away from you. And the light coming to you from this spot at a given instant really doesn't have any forward or backward movement from the actual spinning star. So if a star is rotating fast enough, what we'd expect would be some of the light that would be here is red shifted over here, and some of the light that would be here is stolen and blue shifted. So here's what that looks like in a slit spectrometer. See that? That's the rotational broadening of Altair compared to Vega. This is also done with a slit spectrometer. Okay, just to finish up, how do we get started? Well, you need a grating of some sort. I've talked about the star analyzer. You need almost any kind of camera, mono, color, video, cooled, fits, DSLR. You may need a spacer or something like that because although this distance between the grating and the sensor, how do I get rid of that finger? The grating and the sensor, that distance can't be too great or too close. It's not critical like it is with focusing. And there's a way on our site to figure that out. And a lot of people just send me their telescope and camera names, and I let them know what they need. Here's my software, RSpec. Here's that shareware I mentioned earlier. I'm friends with the authors these days. Remarkably powerful software, very, very steep learning curve. So there's lots of books out there. There's forums out there. You know, that book on the right there, just 2 quick pages I want to show you. Notice that spectrum there. It's nice. It's got all these call outs. It's telling me what I should be seeing. But knuckle dragging programmer that I am, I don't know the significance of nitrogen or any of the other things this is called out. So the great thing about this book, the one that's on the right on your screen, is it's got a lot of text that explains to people like us, not professionals in the field, what we're seeing. It's a great, great book. And there's lots of books linked to on the site under that link button there. The software is free for 30 days. In fact, I taught a workshop to the AAVSO about 4 years ago. There were about 100 people there, hands-on workshop. And they recorded it, and it's on YouTube. So you could download the software and the sample data from that workshop, and then watch the YouTube video tomorrow morning. And you could step through. It's an hour-long workshop. And once you were done that, playing around, you'd have spectroscopy in your bones. It would stick. And instead of it being, yeah, last year we heard this guy who talked too fast and long and didn't have any hair talk about spectroscopy, you'd actually know it and you'd remember it. So it's something to think about. AVSO has jumped really big into spectroscopy. They have an online spectroscopy database. Stella Kafka, their great director now, she and Arnie, her predecessor, are professionals. They know the importance of spectroscopy. So there are some opportunities for pro-am collaboration. There's more coming as these organizations jump up in terms of commitment to spectroscopy. The BAA has a database, the French have a database. So we've come a long way in the last 200 or 300 years, as well as the last, 55 minutes. So I'd like to thank you all for inviting me tonight, for smiling at some of my jokes, and in general for the outreach and the community service that, that many of you do, I'm sure. It's a way we can give back. It's a way we can give forward. You know, I was thinking, this will be the second time I've shared this. I was washing the dishes last night thinking about it. You know, when you're at a star party, for those of you who go to them, it's midnight. You know, what really has sort of impressed me over the years is although there's some people who are really chasing objects, it gets to the point where we're just sort of standing around talking, you know? We're under this cathedral of stars. We're with our friends. They all have common interests in astronomy. It's really a very meaningful social event for us. And, you know, we don't have that opportunity, many of us right now, because of the shutdowns. They'll come back, I'm sure. But I think Zoom can act as a weak substitute, but a substitute that has value to use these meetings in a way that helps people socialize and helps as a community you all stay together. So I hope in addition to the business meetings and presentations like this, that you'll think about using these sessions like that. In fact, let me stop my screen sharing here. I want to show you one thing and then we can get into Q&A. If you're seeing right now a big image of me in the middle with just a thin strip across the top of a few videos, there's a different way you can look at the screen. In the upper right-hand corner, there's a button labeled View. With this, I don't know if it's a Rubik's Cube, this thing, or whether it's a tic-tac-toe board. But if you click on that and select Gallery, you'll see a really different view. And I like this view because you get to see more people at the same time, so it becomes a community. So it's a toggle. You can go back and forth and click on that View button again and go back to speaker view if that's how you prefer it. But anyway, thank you all again. Have a great evening, and I'm here to answer any questions you can have. Thanks for your patience. Thanks. I appreciate it, Dick. So
that was awesome.
Good. So you'll need to, if you want to ask questions, it can be a free-for-all. There aren't hundreds of us here. Feel free to just jump in and unmute yourself and ask any questions you have. I'd be happy to try and answer them.
So Tom, what programming software do you use? You say that you program a lot as well. Is there a certain language you use or software? Or?
Yeah. What language do you use, if I may ask? What's your prominent language?
C++ and Python.
Okay. Are you doing astronomical software with a Python, or what are you using the Python for?
Right now I'm a double major in data science and aviation sciences.
Wow.
And I want to study, I'm going on to get my master's in computer science to study simulations and video game design.
Wow, fantastic. Very cool career path. Not dissimilar to mine, although mine's a half a century older. Longevity doesn't mean merit. It just means you managed to do the same, dig the same ditch for a lot of years. I'm programming, and the reason I asked you was trying to deflect having to answer, which I have no choice to, because I'm going to tell you it's not C#, which is what would, I'd go, oh, I'm pretty good, C#. It's Delphi. Delphi is not Visual Basic. Delphi is essentially the predecessor to C#. Lots of the same object-oriented development and encapsulation and polymorphism and all the things that you may have encountered. So that's the language I'm programming in. And it's worked out really well. It's all only way I can show video and extract all that pixel data and do all the graphs is to have it all massively threaded. So it's all multitasking. Other questions?
Thank you.
Sure, thank you, Bear. Hey, well, who's that standing next to Saturn over there, next to Stephen? That's pretty cool. I love that background.
Say hi.
Yeah.
Nice.
Say hi.
Hi.
Hey, how you doing?
Hi.
Good. Great. Thanks for dropping in and saying hello. So you didn't get to see, I don't think you were there earlier, but I, as a professional, it's important that I dress for success, So, are you laughing at me? What's going on here? There shouldn't be any laughter, and this is a serious business. We've got to learn, right? Anyway, thanks for the smile. Other questions?
But just a statement, if I may.
Please.
Brad Riza.
Brad, how are
yes,
you?
I'm good, and I just wanted to say thank you.
You're welcome. This is a guy, I've told you this, Brad, so I can confess to the group that when he first bought this stuff, I get this stream of people buying stuff, and for some reason, there's something, did you buy like the classroom device, Brad? Was that the first thing you bought?
No, I bought a grading first.
Okay. Somehow he impressed me as being a guy I wouldn't be hearing much from. Probably because, he couldn't get it going and I couldn't, he didn't ask questions. And I know that's not a very complimentary thing to say, but as it turns out, he blew my socks off with the stuff he was doing with the grading. To me, it's just such a pleasure when I see somebody go from 0, not even 60, going 0 to 30. That first spectrum you get of Vega with those dips is just mind-blowing. It really is. So thanks for saying something. Hi, Brad. I'm sorry I didn't.
Yeah.
Oh, you've got that too. So that's a little handheld device. What do you use that on, Brad?
I use it for star parties. Well, I do a lot of solar observing.
Yes.
And so I'll take it out, and I, of course, don't point it at the sun, but I point at reflections.
Yeah.
And you can see the spectra. I use it around the house to look at light bulbs and decide which ones I want to keep and which ones I want to throw away.
Nerd. Oh, yeah, that's a great. I love it. I want to share my screen for a second since you mentioned the sun. I forgot I wanted to show this. So if you're doing solar outreach, that's not what I wanted to do. That's what I wanted to do. If you're doing solar outreach with a hydrogen alpha scope, and a lot of us do that. I jealously guard my sleep hygiene these days. I don't want to spend the whole night out. I don't have that commitment anymore. So when I'm out there with my my lunt and I'm doing outreach, I love to do it. This is a tool that you can use as a secondary telescope, especially if you have a Q and you've got somebody else to mine this. This is from Shellyak. It's called an L high-res light, and you can see it's a spectrometer. And I'll show you an example in this video. I just want to make sure I am sharing my screen, right? You can see that that device. Yes. Okay, thanks. And because it's got a slit inside of it, you can only see a small piece of the spectrum. And so this lets you tune what little window you're looking in through. And right now it's pointing at magnesium. Magnesium actually has a triple line. It's called the magnesium triplet. So let's start this video. It's a bad example of how to make astronomical videos, because literally it's just my iPhone up against the eyepiece. But as we zoom in there, you'll see there's the magnesium triplet right there. Those are all different lines. And you can actually grab that lever as I'm about to do here, sorry for the audio in the background, and sort of tune through different colors. So there's hydrogen.
You see if I can get the.
While I'm talking there, that little gnomon there lets you point it. You don't even need tracking. There's my shoes. One more example here. There is the sodium doublet that we saw on NeoWise in my presentation. So the only downside to this is it's not cheap. It's about $1,200, I think, and it's a one-trick pony. But it's a tool that you might think about using when you're doing solar outreach. Anyway, sorry for that diversion. Other questions? People have anything you want to discuss?
So we have a 24-inch Ritchie Chin, and we have an SA200.
Okay.
How is that different from the SA100?
Good question. The Star Analyzer 100 and 200 just differ in the number of lines per millimeter. With a big telescope, typically you need more dispersion, and that's the kind of thing that if I don't know, have you used it, Dick? Has it been used there and people gotten decent stuff?
No, it hasn't really, because we haven't had anybody really know what to do with it. And we have a Princeton Instruments camera that is strictly monochrome.
That's okay.
I'm assuming that you know, we don't need the color imaging to do the spectrum.
Correct. 24 inches is really big. When you don't have a slit, the challenge is that the star size affects your resolution. And of course, the star is going to be pretty big. It's probably a pretty big full width half maximum star. So if you want to email me, I can and tell me what the focal ratio and the camera model is. I'll let you know mounting, how to get that thing mounted on the camera.
Okay.
So typically you get up into even 11 and 14 inches. Things get a little dicey without a slit, but I know people have done things with the 24. It's pretty amazing to do. And the thing is, when you split the starlight, the good thing about the 24 is normally when you're imaging, the photons from the star fall on a handful of pixels, right, on your sensor.
Right.
But when you split off that light with a grating, now you have the same total number of photons spread across hundreds of pixels. So you lose about 5 or 6 magnitudes. So having a lot of aperture helps. I've done this kind of thing literally in the city lights outside the portico of a Marriott hotel or a Holiday Inn with my laptop on the hood of my car. So I mean, with bright stars, you don't need dark skies.
Right.
So or big aperture.
Right.
Anyway, I'd be happy to help you all get that thing going.
Okay.
Anything else? Well, listen, I'd like to thank you all again. I appreciate the opportunity to speak to you tonight. I hope that you were entertained and learned something. Bear, I loved hearing about your career and the direction you're taking. That's really exciting. Python, the reason I ask about Python is because Python, of course, is used in a lot of astronomical calculations. The interesting thing from what I've heard is that a lot of the core code that's available to astronomers is still in Fortran. Because it was written 3, 4, 5, 6. Oh, Brad's touched Fortran. So have I. I suspect Brad has actually handled punch cards as I have, haven't you, Brad?
Yeah, I did my master's thesis with punch cards.
That's wonderful. You too, Dick. That's great.
Dick, you have us all muted.
No, I don't have
you
to
muted everybody. You can unmute yourself.
Oh, good. Yeah, you can always unmute yourself by hovering over you. It looks like everybody's unmuted now, though. Your mic was just a little. I don't know, that headset's been giving you trouble, hasn't it, Brad? Yeah, we can, but not very loud. It was too loud earlier on this evening, but now it's not loud enough, I don't think.
You're unmuted, Brad.
Okay, so actually the SA200 works really well on our telescope.
Good.
I've used it 4 or 5 times, but my question is that the x-axis calibration is pretty easy, right? You look at Vega.
Wait, your mic just cut out.
Yeah, we're losing you, Brad.
I think you have a bad connection on your
You
mic.
may have a bandwidth issue.
Bandwidth.
Oh, okay.
I'm on DSL.
Oh, okay. It's okay now.
Okay.
So x-axis calibration is okay, right?
Right. What about the y-axis calibration?
There's a video on that. It's called on our site. It's called Correcting for Instrument Response, and it's not that hard to do. It's interesting because then you get to see the shape of the Planck curve, the Planck-like curve of the star. Professionals actually don't use that shape, that called the spectral energy distribution.
Right.
They actually use features. But there is a video on it, and I'm happy if you send me a sample sometime, if you drag out that star analyzer, I'm happy to sort of process it and give you my feedback on the exposure and tracking and all that stuff. I'd love to help.
We don't have to drag it out. It's mounted in the filter wheel.
Go for it then. I want to see a sample by the end of the week.
Maybe.
Well, you know, this sort of reminds me of that old movie scene where there's a whole bunch of soldiers lined up side by side, and their commander asks for a volunteer, and everybody steps back but one. And that one is standing there looking like, hey, what happened? Where'd everybody go? So that's you right now, Brad. But anyway, I'd love to help any way I can.
Yeah, we'll
All
come
right.
up.
Okay.
Good. Thanks again. Yes.
The presentation at AVSO was fabulous.
Oh, I'm so happy to hear that. The problem is, you know, it's like when you hear a comedian and everything they say sounds like spontaneous. It's just a conversation and they say things like, oh yeah, you know, I've met with comedians, you don't want to see the same comedian 2 nights in a row, because then you discover just how unspontaneous it is. It's rehearsed unspontaneity. And so you've heard my talk twice. And so hopefully there was enough gap in there where some of the information was seemingly new.
Well, it was certainly very informative, Tom, and we really appreciate you coming in and spending your time with us tonight. And I know everybody's appreciated. Let's all give Tom a big hand for joining us tonight. Thank you, sir.
Thanks so much. Have a good evening, everybody, and take care and stay safe.
Okay.
Don't forget to vote. I won't
That's
say
right.
anything more about it.
And
See you.
already.
Bye.
Okay, I'm going to end the Zoom meeting now unless anybody wants to jump in with one last thing. Hearing nothing, we're gone. Good night, everybody. Thank you.
Good night.
For coming.
Thank you so much.
Bye.